I might call your spot pumping if you got crushed ice in a styrofoam cup with the refill right. So homie, no time to chill, we got places to try.
And welcome to the video on Lagrange multipliers, aka optimizing with a constraint. Okay, so sometimes we want to optimize or find extreme values of a function, f of xy, when it's subject to a constraint known as g of xy. So let's say we have some function. This is our main function. Okay, that's what I consider is a main function. Okay, that's the one we're mostly concerned with. This is the one we want to optimize. We want to optimize, okay, which is find the maximum or minimum of something. Minimize. Sorry, not minimize, optimize. There we go. We want to optimize, right? But we have some kind of constraint. But we have a constraint, and this one I usually write it as g of xy or something, but we have a constraint g of xy is equal to 0 that we must abide by or follow, right? So I kind of think of this guy, the constraint one, kind of like railroad tracks that we must stay on. We can't derail ourselves just randomly. So these are like railroad tracks that we have to, they kind of impose a limitation on where we can move in order to satisfy this f of xy. Okay, so let's start with an example. So what we're going to say is, here's a really good one. We're going to find a point on the line 2x plus 3y is equal to 6, closest to the origin. Okay, so let's see. Well, first of all, this graph looks like something like this, let's say. So let's say we have it's going down in some kind of slope here, okay? So here's our x and there's our y, and what we want is, so here's our origin, right? So this thing here, this graph, is what we're allowed to move on. That's like the range of where we're allowed to move, okay? So this is like our railroad track, literally. It's just like one line that we can move on, right? So this is our railroad track. So this is our g of xy, but it's not there yet because we want our g of xy to equal 0, right? So we're just going to move that 6 over to the left side, and now we get that 2x plus 3y minus 6 is equal to 0. So now it is formally, this thing is our constraint curve, because that's what we're restricted to move on, okay? So now, what we want to do is actually, the point of this is, our goal is to minimize the distance from the origin, right? So we want the closest point to the origin. So if we start out here, that's not necessarily the closest, right? And then if we keep moving in, that's not the closest either. And we're getting there, but the closest would be somewhere around here, right? But anyways, we want to find that point. So how are we going to do that? So first of all, well, we found our constraint curve, right? So this is the constraint curve, okay? And then we actually want to minimize the distance, so we can kind of just make up a formula for the distance, right? Because we know what the distance formula is, especially with regards to the origin. So it's just going to be this, right? So this is our main function. And what we want to do is minimize this. We want to minimize. Minimize. Okay? So that's what we want. And we have our constraint one. So now we want to know where is f of xy, this function here, where is this a minimum? Where is it the lowest value on our constraint curve? Okay? From the set of all points on our g of xy line. So now I'm kind of going to go off, not really on a tangent or anything, but I'm just going to go off on our graph here and say that our level curves, so this is more or less like a proof of where we're going to get the Lagrange multiplier from. So this isn't really necessary to know how to prove and stuff, but I'll just show you guys so you can understand the concept behind it. So our f of xy, our main function, right, level curves of this, so that means when something's a constant, when our z or whatever, when that's a constant, when this is constant, that means if it equals a constant, that means the distance is a constant from the origin, right? So, for example, through this point, the level curve looking through this point would look like a circle, right? Because then on a circle, that means that centered at the origin, at all of these points, we're at the same distance from that origin, right? Same distance, same distance. So this is a level curve level curve of our f of xy, okay? And another level curve would look like, let's say through this point, it would be another circle, right? But just with a smaller radius, a smaller distance from the origin, okay? So this is another level curve, etc., etc. Okay, so something like that, all right? But now, what's the important part is that we're going to make use of our gradient, what we know about the gradient. So we know that gradient of fp at some point p points in the direction in order to get to the next level curve the fastest, okay? So that the fp points in the direction of greatest increase. So this points in direction of maximum increase, of max increase. So graphically what that would look like is, let's say we're starting at this point, this leftmost point here, okay? So to get to the next level curve, we would point straight at it, right? So this would be our our gradient of f, okay, at that point. Now, once we move, let's say here, since we're still on that line, right? Sorry if the graph is a little bit seedy, but now it kind of changes direction, right, as we're moving along the line. So then, for example, this one here, this point, this closest one that I'm filling in, it would point kind of more straight toward the middle, right? Until we get to finally our point. Let's say this is the one, that one right there, okay? So then our gradient of f would point directly at the origin, okay? So anyways, the point here is saying that when we do reach this local minimum of f on the constraint curve, on our line, that happens to be where the gradient of f, so here's the important part. So this point here, that one right there that I'm circling, the gradient of f at that point p, so I'll name this point p. Again, I'm sorry that the graph got so busy in there and so chaotic. But anyway, so the gradient of f at the point p is parallel to the gradient of g, of our constraint curve at that same point. So g is actually going to look something like this. It'll point the other direction, but in some way it'll be on the same line, right? So on this line here, that's where both gradients live, okay? So I'll expand upon this concept on the next slide. So what that means is if gradient of f at some point is parallel to the gradient of g at that same point, that means that they lie on the same line, right? So if, like, for example, this is our gradient f at p, and then here was point p, right? And then gradient of g, they don't have to be the same length or anything. It's just they lie on the same line, right? So if they're on the same line, as far as vectors go, that means that they must be scalar multiples of each other, right? So that means that these two must be scalar multiples of each other, right? So here we're getting closer, right? We see the word multiples. So what that means is it's going to lead us to the equation gradient of f at p is equal to some lambda, so some constant, right? Some multiple of gradient g of p, okay? And we've made it. This is our conclusion, basically. This is the all-important Lagrange equation, okay? Lagrange equation. All right, and this is for optimizing with that constraint curve of g. But and then also, just a side note, this lambda here, or whatever you decide to put in there for the variable, this is called your Lagrange multiplier. Lagrange multiplier. Okay, so that's basically it. That was the takeaway, is this all-important equation here. I just wanted to show you guys some background on how we got there.
And right around the corner is why not? It's awesome. Mel's got Astros, and that's that. I only mess with Fat Burger if your fries are fat. Now Whittier got rubies. They're renowned for the shakes.